Hello and welcome back to my channel ConQuiz series. Today is ConQuiz 14. We have already started the concept booster series on quantum. Today is part 2, and like the part 1, today we'll be discussing some short conceptual questions. We call it part B. Okay. The concepts like well-behaved or acceptable wave functions, coordinate systems, standard deviation, uncertainty, quantum postulates 3, and correspondence principle. So these are the concepts that we'll try to cover today. We'll start from something continuing from ConQuiz 13. The question was relate rho d tau and rho d tau integration. So as we discussed that rho is the probability density psi star psi or mod psi square, and rho d tau is the probability in d tau. So now the first question of today's video, function is given. Of course, it's a one-dimensional wave function. Now the question is, what are the units, if any, for the wave function of a particle in a one-dimensional box? So one can easily say that from this expression itself we can deduce the unit, and it is 1 by L to the power half, that means length to the power minus half, right? But from probability point of view, if the function looks very different, even then how we can answer the same question. Okay, now rho d tau is psi star psi dx, right? And that is the probability in some d tau unit or dx unit. So probability is unitless, so psi square dx would be unitless, so psi square must have the unit of dx inverse, right? That means length inverse. So if psi square is length inverse, then psi must be length to the power minus half. So the unit of psi is length to the power minus half or meter to the power minus half. Now if it's a three-dimensional box, then of course it would be L to the power minus 3 by 2, right? So that is how we can use the probability concept here. Well, the next question, fix the fix. It looks or sounds like a rhyme. As you know that from Schrodinger's solution, the wave functions that we get, it may not be well behaved to start with, but if we can impose some mathematical criteria on the basis of some physical requirement, then only we call the functions well behaved or acceptable functions. So what are those mathematical criteria? FICS. So we have to fix the FICS fix. So what do they stand for? FICS. Let us see first. F for finite, that means the wave function has to be finite, psi. I integrable, square integrable. C continuous, the wave function and its first derivative have to be continuous, and the wave function must be single valued. So the criteria, all the four criteria, actually because of a single reason, and that is the definition of probability density. That's mod psi square is probability density of finding the particle at a given point at a given time. Now if it is so, then of course it has to be finite, right? Why a function, I mean probability density should be not finite at somewhere? So it's a very common sense requirement that it has to be finite. Why integrable? Because mod psi square d tau integration, it gives you total probability. So if the function itself is not square integrable, then it's meaningless, because you can't find the total probability in that case. So it has to be square integrable. Continuous, of course the same reason, a common sense reason you can say, that why the probability density should be discontinuous at certain point. There is no reason, right? So it has to be continuous. Of course there is a mathematical criteria that I'm coming later on in a while. And single valued, again the same reason, because mod psi square is probability density, and if psi is not single valued, then psi square would be multiple valued. That means at a given point and given time, there are 2 or more than 2 probability, which is absurd, right? There would be a single value. So psi has to be a single valued function. Continuous, I told you that some mathematical criteria is there behind the whole scene. Why continuous? Because mathematically we know that if d psi dx has to exist, then the psi itself has to be continuous. Similarly, if the second derivative has to exist, that is d2 psi dx2 has to exist, then its earlier one, that is the first derivative, has to be continuous. Now, why these two derivative, first and second derivative of psi, have to exist? Because you know, momentum operator, it corresponds to d dx, and Hamiltonian energy operator, it corresponds to d2 dx2. So p psi or h psi, in these problems, the first derivative of psi and the second derivative of psi have to exist, and that's why the earlier derivative, that is the psi itself in the first case and first derivative in the second case, has to be continuous. So that is the pure mathematical reasoning. Now a few problems you can easily see. Some functions are given, and you have to check the range is also given, and you have to check whether these functions are acceptable or not. Well, if you can find any one of the 4 criteria that is not valid for the given function, then you can declare that this is not acceptable. But otherwise you have to check all the 4, which is a bit tedious mathematical job. Then we can look for a solution, and you can explore it later on. I have taken it from Macquarie-Shyman. The answers are given. E to the minus x is all 4 criteria are valid: single valued, continuous, finite, and integrable over the range 0 to infinity, but not over the range minus infinity, x equal to minus infinity. So this is not acceptable, the same function. Sin inverse x is obviously multiple valued, not acceptable, but the next one is acceptable, remembering that sin x by x in the limiting condition x tends to 0 is actually finite. And the last one is not acceptable because the first derivative at a given point within the range is not continuous, right? E to the minus mod x is not continuous at x equal to 0. So it's a bit tedious mathematical job, but these are the solutions of the problem. Okay, so now let's go to the next. We'll discuss something apparently different, but actually conceptually and application oriented. They are interrelated, and that is coordinate system. As we know, our physical space is 3-dimensional, so we need a 3-dimensional coordinate systems, and the very popular one is the Cartesian coordinate system x, y, z. So suppose a point is there, and you want to visualize where the point is in the space, and you need a reference frame, x, y, z Cartesian coordinate system. Here the origin is, and the position x, y, z, as we know, its usual significance and meaning. But the point is that Cartesian coordinate is not the only coordinate system. There is there are many other coordinate systems. For example, spherical polar coordinate system. Again, we need 3 variables or parameters, and now it is r, theta, phi. So from the figure, it's very clear that r is the distance from the origin of the point, and theta is the angle between the vector, this point vector, and the z axis. And if you take a projection of this point on the xy plane, and that makes a phi angle with the positive x axis. So that is how we define r, theta, and phi. Of course, and obviously, this r, theta, phi are connected to x, y, z. Like these are the relations. You can, a little bit of geometry can give you the answer that how they are related to x, y, z. And the reverse relation is also there. That means how r, theta, phi you can get from x, y, z. So that one can easily check it. And what are the ranges of x, y, z? R, theta, phi? Obviously, r can be from 0 to infinity, any value, but theta is restricted to be, because it is around a z axis, so theta is restricted to be 0 to pi. So 0 less than theta less than equal to pi, and phi is on a plane, so the whole plane angle, that means 0 to 2 pi. That is the range of phi. Okay. Now we can explore immediately a question that describe the graphs of the following equations where r is 5 constant, theta is pi by 4 and phi is pi by 2. So the first you see r equal to 5 irrespective of theta and phi, that means it's going to give you a sphere of radius 5 centered at the origin. Now theta is pi by 4, so that this angle is pi by 4 irrespective of phi. That means it is going to give you a cone about the z axis, ice cream cone about the z axis of internal angle theta equal to pi by 4. Well, phi is pi by 2, so this phi is pi by 2, that means this angle, the whole XOY angle, and that is irrespective of theta, that means it's the whole plane on the YZ. So it is the answer, the YZ plane, right? So let us go to the next. It's a numerical problem, that conversion between one to the other. Find the XYZ coordinates of the point with spherical coordinates r is 1, theta is pi by 2 and phi is pi. So it is simply application of the formula. Answer is -1 0 0. You can easily check. Just apply the formula of x, y and z and you will get the answer -1 0 0. Okay. So this is just an example to understand the coordinate transformation. That's very interesting, a formula from childhood. If you ask class 5, 6 or 7 student that what is the formula for finding the volume of a sphere of radius a, he will or she will immediately answer that it's very easy, 4/3 pi a cube. Or what is the surface area formula, they will say 4 pi a square. But if you ask that how do you get it, probably they will keep silent, and here we can explore a little bit. So this is the explicit picture of a sphere is there, and we have taken a slice of a cake like thing. Here separately it is mentioned. So the slice position is actually at an angle theta, and if you call it length, then it is the d theta. Okay, and similarly if you call it width, and then that is d phi. Okay, d phi, and there is a thickness dr. So length, width and thickness we can see from the figure are like this. So let us see it separately. R sin theta d theta d phi, r sin theta d phi is you call the width, or length is r d theta and thickness is dr. So what would be the volume of this slice of cake, right? So just multiply the three factors. So r sin theta d phi, this one, into r d theta into thickness dr. So it gives you finally r square sin theta d theta and then d phi. So r square sin theta d theta d phi and dr also. So this is the volume element, small volume element dv. Now what would be the total volume? Then of course it's a question of integration. How do you do? You have to integrate over the whole theta range or phi range, that is 0 to 2 pi and 0 to pi. That would give you 2 pi from here and 2 from here, so that is 4 pi from these two last parts, and r we are integrating but over the limit 0 to a, not infinity, because I want the radius to be a. So if you see the result, it is 2 into 2 pi into r square dr gives you r cube by 3. That means after putting the limit you will get a cube by 3. So this is 4/3 pi a cube. So that is how we can get the total volume of a sphere just from this small volume element in polar coordinate system. So you can immediately ask that what about the area, surface area. So let us see it from a different point of view. If you integrate the last equation, that is dv, over theta and phi but not over r, so r square dr is left outside the integration and we are integrating over theta and phi. So what we get? 2 from here and 2 pi from here, so 4 pi r square dr. So 4 pi r square dr. So this is the volume dv. Obviously dr is the thickness, so that means it is the volume of a spherical shell of thickness dr, and the surface area is 4 pi r square, right? So this quantity is the volume of a spherical shell of radius r and thickness dr. The factor then 4 pi r square represents the surface area. Okay. Now the question is, can we get it directly from some other way? Surface area formula 4 pi r square. Yes, there is a formula. If we consider the same figure and just ignore the dr part, thickness part, then we get the orange part, that means the area. So that is 4 r sin theta d phi into r d theta. So if we call it dA, then dA is r square sin theta d theta into d phi. Okay. Now by same way, if you integrate, then you will get 4 pi a square. To 4 pi from this theta pi part, and r square, if you put r equal to a, so that means you will get the surface area of a sphere of radius a. Okay. I think it sounds very interesting. Now I have two quick problem. Determine the volume of a hemisphere. So hemisphere, half of a sphere. So naturally you will be integrate the dv, but not using the whole range of phi, but half of the range, because you need the half of the sphere. So 0 to pi is replaced by 0 to 2 pi is replaced by 0 to pi, and that gives you 2/3 pi a cube. Okay. Similarly, determine surface area of a hemisphere. So surface area, again you can start with the formula of surface area dA, and then if you integrate over theta and phi and leaving r is replaced by a, so that would be again 2 pi a square. So obviously the results are very correct, because 4 pi a square is the total surface area. So obviously by 2, that means 2 pi a square would give you the area of the hemisphere. Similarly, 4/3 pi a cube divided by 2, it gives you the hemisphere. So it gives you an understanding that how to use the range whenever the situation arises. Okay. Well, we are switching over from this coordinate system to something we call standard deviation. It's a very multi-dimensional, I mean omnipresent some concept, standard deviation. And why is it important in quantum mechanics, right? So let us first start with the definition of standard deviation and where does it arise. Suppose you measure something so many times and you get exactly the same value all the time, then there is no distribution. The average would be the same as we are getting the single values. But because of some reason, if you measure something and you get different values at different measurements, then there is a question of taking an average, and there is a question of distribution of the values that you are measuring. And if you plot the number of times that you get some particular value, so those values against the number of times you get the values, that would give you a beautiful distribution pattern or distribution curve, and that distribution would have a spread of around the mean, because all the values are not same, so there would be a spread around the mean, and that spread in quantum mechanics is related to uncertainty. For example, here this is the famous Gaussian distribution, and this sigma is actually the parameter, we call it standard deviation. Sigma square is called variance, and you see that there is a spread of the distribution. Okay, spread of the distribution, and this is the mean position. So this is Gaussian distribution. Now, why are all this important in quantum mechanics, right? First of all, mathematically, what is the prescription for the definition of this standard deviation, delta A? First, let us call delta A square the variance, and this is defined as an average quantity. Average of what? Average of some square. What square? It is the difference between the measured value and the mean value. So A minus A average, its square. Obviously they would be different for different measurement, because A itself would be different for different measurements. So if they are very different from different measurements, then you can take an average. So that red color average is the final average. That gives you the variance. Now the question is here, starting from this definition, we can reach a very a very practical, useful expression that same delta A square is equal to A square average minus A average square. And if you get all the time the same value in your accurate measurements, then you can see that the A average and its square is exactly the same as the square average, and that means there is no distribution. That means there is no standard deviation, right? No spread of the distribution. So delta S would be 0. Okay. So is it justified, this expression? Of course, and obviously it is justified. You can explore on your own, but it is justified that the definition that we start with is actually gives you A square average minus A average square. Usually we use this formula. Okay. Now a little bit of move from quantum mechanics and relation to standard deviation, etc. We know that a property of commutation of two operators. If two operators do not commute, then their corresponding observable quantities do not have simultaneously well-defined values. Simultaneously well-defined. That means there would be a spread of values. Say A and B, so two operator and corresponding to properties. So sigma A and sigma B are the standard deviation, and if they do not commute, the operator A and B do not commute, then there would be an uncertainty because there would be spreading of the values and standard deviation. And in fact, it can be shown by rigorous mathematics. I am skipping that part, that there is a relation like this. So sigma A and sigma B square, that means variance product of A and B, that would be greater than or equal to some quantity, and that quantity involves the commutator. So if the commutator is 0, then the whole right hand side is 0. That means the product is 0. That means there is no standard deviation, no uncertainty in either A or B. But if they do not commute, then there must exist some non-zero sigma A square and sigma B square. Okay. So let us see an example. A and B. Let us take A to be the linear momentum operator and B to be the position operator. So momentum and position. And as we know that they do not commute, and the commutator value is minus IH bar. I is the unit operator. So if we just put this value in this integration, so what we will get? Psi star minus IH bar psi and then whole square. So minus IH bar, it will come out to give you minus IH bar square, and psi star psi remains. So psi star psi remains means that is the normalization condition, as you know, that gives you 1. So the final result is minus I square is okay, minus 1 and minus minus plus, so H bar square by 4. So sigma P square sigma X square gives you H bar square by 4. If you take the square root, then it is actually H bar by 2. So sigma P and sigma X product gives you the H bar by 2, and which is the celebrated famous Heisenberg's uncertainty principle. So it is connected to somehow this standard deviation concept, which is related to uncertainty in quantum mechanics, and that all starts from this commutation as well. So many things are in a single slide. You please explore later on your own. Now, in relation to this standard deviation, again, I would like to bring the postulate 3, quantum postulate 3. What does it tell? In any single measurement of the observable that corresponds to the operator A hat, the only values that will ever be measured are the eigenvalues of the operator. So A is the operator. If it satisfies some eigenfunction equation, then some eigenvalue would be there, and whatever times you measure the operator, I mean the quantity A, you will get one of the eigenvalues, right? That is postulate 3. It is taken from a separate text. In any measurement of the observable associated with the operator A hat, the only values that will ever be observed are the eigenvalues A, which satisfy the eigenvalue equation. So whatever the time you measure the quantity A, you will get the value small a. Okay. So that is the postulate 3. Now we can see from the standard deviation point of view the same postulate. Well, suppose that psi must just happens to be an eigenfunction of A. So we can write A psi n, A n psi n. So there is a set of eigenfunctions and a set of eigenvalues A n. So what we will do? We will take the average of A, right? So by simple definition of averaging, this is the definition: psi n star A psi n, and A psi n is A n psi n. So A n psi n, and A n is a value, so it comes out of integration, leaving psi n star psi n, that is 1. So the final value is AN. So average A is nothing but AN. Now what about A square average? So A square psi n is A psi n, and A psi n is small an psi n. It comes out. So again A hat psi n, that gives you another an, and finally you will get an square psi n. Now you take the average. So A square average by definition is the functions enclosed by A square operator, because A square psi n, as we have seen, it is an square psi n, so that would come out leaving psi n star psi n, which is 1. So now you get an square. So A square average is an square and A average is an, so A average square is an square again. So you get an square minus an square, and that is 0. So what we see that the practical definition of standard deviation or variance is A square average minus A average square, and here we see that the result is 0. So sigma n square is 0. That means standard deviation is also 0. Okay, that means you get the result says that the only value that we measure is the value an. Okay, however, the system is not in a state described by an eigenfunction. If it is so, then one measures a distribution of values whose average is given by postulate 4. That is another postulate. That means if the system is not described by a state which is an eigenfunction, in that case what value you will get? Then we of course we will not get the eigenvalue, but we will get an average value. So let us see a problem on averaging. Suppose one-dimensional box problem. Average energy is given by this formula, and you have to find the p square average from this result. Okay, so it's a bit tricky but simple question. How? Because you know that E in 1D box problem potential is 0, so total energy is nothing but the kinetic energy, and that is p square by 2m. So average E is nothing but average of p square by 2m. M is a constant, so Tm is coming out. So it is simply p square average, and that is equal to the given quantity n square h square by 8m a square. So from here you can easily equate these two to get p square to be n square pi square h bar square by a square. So that's a simple question. You can take it as an exercise. A demonstration of postulate 3 that you can take as a home task actually. The question is like, so by direct calculation that sigma E square is E square average minus E average square, and that is 0 for a particular box for which psi n x is given. So the system is described by a function, but as you know that function happens to be the eigenfunction, as you know that. So of course if it's an eigenfunction, then you will get the eigenvalue. So in that case every time you will get that eigenvalue, and hence E square average minus E average square should be 0, and there would be no standard deviation. But here the question is that you have to calculate directly. That means you have to evaluate the E square average, you have to evaluate the E average square, and then you show that this is equal to 0, and really you will get the answer to be 0. Okay. If we measure Lz of a particle that has angular momentum quantum number L equals to 2, what are the possible outcomes of the measurement? So the question is that what we are measuring? Lz, right? Angular momentum quantum L equal to 2 is given. So as you know that the L square operator, its eigenfunctions and eigenvalues, there are a number of eigenvalues depending on L and depending on more precisely m values, where m is connected to L, minus L to plus L. So for L equal to 2 there are 5 m values, minus 2, minus 1, 0, plus 1 and plus 2, and the eigenvalue for Lz operator are nothing but this m h cross, that means minus 2h cross, minus h cross, 0, h cross and 2h cross. So these are the eigenvalues, and naturally if it's an eigenfunction, so the outcome of measurement is of course one of the eigenvalues. So the answer is for L equal to 2, the possible eigenvalues of Lz are minus 2h cross, minus h cross, 0, h cross and 2h cross. Only eigenvalues are the results of measurement because it's an eigenfunction of Lz. Finally, the correspondence principle. This is a very famous Bohr's correspondence principle. And what does it tell? Before we see the principle, let us see the figure. This is the chi-square plot versus x in 1D box problem, and this is the ground state n equal to 1, then 2, 3, and so on. And as you see that in the ground state, chi-square is the probability density, so the particle is most likely to be around this middle point of the box. But in case of n equal to 2, it is most likely to be here and here. Okay. So that means quantum mechanically, the particle, as if it has some bias, it has some priority or choice of its own, that where it would be more likely to be present. So that we see that's in this priority of or choice of particle, that is the quantum feature. In classical, there should be no such bias or choice. There should be an uniform distribution of probability, if you say so, right? But the question is that is there any condition or situation where these quantum results and classical results, they converge or merge together, they tend to be the same? The answer is that is given by the correspondence principle, and that here it is for n equal to 20. So as you see that at the ground state it is mostly likely at the middle, but in the first, second, the distribution is slightly spreading. Okay, and in n equal to 4 it is even more uniform compared to the ground state, and for n equal to 20 we see almost that there is almost not a one or two choices, but so many choices. That means it is gradually converging to the classical picture. So that is the correspondence principle. This result illustrates that according to which quantum mechanical results and classical mechanical results tend to agree in the limit of large quantum numbers. The large quantum numbers limit is often called the classical limit. So quantum is of course a very different world, but what we can perceive by our open eyes is the classical world. But a quantum is a two-way journey. You can reach from quantum to classical, and in the limit of high quantum number. So that is the Bohr's correspondence principle. So thanking you very much again. Our next video, session 515, will be coming soon, where we will be discussing quantum postulate 2 and a very important property of an operator, Hermitian and of course anti-Hermitian operator, and all that in the next part. So thanks again. Please keep on watching. Do subscribe. Encourage your friends to subscribe. Thank you.